In this video, let us talk about Coulomb's inverse square law of magnetism. It's a very easy concept. It is not at all a rocket science, very easy concept. And in electrostatics also there is a Coulomb's inverse square law in magnetism as well as. Now here I am going to consider two cases and taking here the two bar magnets in case number one, and these two bar magnets are kept at a distance r from each other. And so here is the distance r between the two bar magnets. And when the similar poles are kept facing each other, then there is repulsion. And they repel with certain force, so we say force of repulsion. In the second case, I have kept the north pole and south pole facing towards each other. Here also they kept at a distance r from each other. So when the different poles are dissimilar poles facing each other, then there is an attraction, and they attract each other with certain force called as a force of attraction. So here is in case of repulsion, there is a force of repulsion, and in case of attraction, there is a force of attraction. Coulomb inverse square law talks about force of repulsion, either force of repulsion or force of attraction. So we talk about force of repulsion, force of attraction in case of Coulomb's inverse square law of magnetism. According to Coulomb's inverse square law, either the force of attraction or force of repulsion, it depends upon the value of pole strength. And pole strength is measured in Ampere-meters, and we take plus m for the north pole. Small m is nothing but stand for pole strength. It is denotation for pole strength. This is a very popular symbol for denoting pole strength of magnet is a small m. So plus m is taken for the north pole and minus negative pole strength for the south pole. Here we got two magnets, first magnet and second magnet. M1 is the pole strength of first magnet, M2 is the pole strength of second magnet. And there are the two cases, as I said, the south, north. That is in case number one, similar poles facing each other, so there is a force of repulsion. In second case, dissimilar poles are facing each other, and when dissimilar phases of magnet kept opposite to each other, there is a force of attraction. Now, for the first magnet, as I said, pole strength is M1, and for the second magnet, pole strength is M2. Here, Coulomb's inverse square law of magnetism is applicable for both the cases, for repulsion as well as for attraction. And according to this law, the force of either repulsion or attraction depends upon the product of pole strength, that is M1 multiplied by M2. So either the force of attraction or the force of repulsion depends upon the product of pole strength. As the product of pole strength increases, the force also increases. So we say the force of attraction or repulsion directly proportional to product of pole strength. And second one is this force inversely proportional to square of distance between them. As the distance is decreasing, the force will be increasing. It is valid for both cases, for repulsion as well as for attraction. So we got here the two equations, and now we'll combine both these equations. So F is proportional to product of M1 M2 divided by R square. Now to delete this proportionality symbol, we write equals to. When we write equals to, we must write k is something constant, M1 M2 divided by R square. This is the constant of proportionality. K is nothing but constant of proportionality. And the value of k is given by 1 divided by 4 pi mu naught mu r. Now it is multiplied by M1 M2 divided by R square. In this expression, F is force of attraction or repulsion between given two magnetic poles, and mu naught is equal to permeability of vacuum, which is equals to 4 pi into 10 raised to minus 7 Henry per meter, and mu r relative permeability of given medium, and mu naught mu r is equals to absolute permeability. Now there is a question for you. Can you apply the same formula in vacuum? If your answer is yes, if your answer is no, then please support your answer with certain reason. Meet you again with next video. Till then, wish you good luck. All the best.